Yes. So, sorry for the late start. Welcome to the 5th lecture, Introduction to Lattice Boltzmann Methods. Everything going? I hope so. Microphone is on. Yes. Okay. Okay. So today we actually come to really to Lattice Boltzmann related stuff, and I hope you can then start doing some work. But before we get there, I remind you that we had last time I made a mess with the Mach number, so I guess I have to repair this somehow. Yeah. Update last lecture. So I said I could not explain. We had this problem that I was basically saying that CS square is proportional to 1 over Mach, and I could not explain why this is the case. So one thing that you should probably remember for life is if you get to a scientific fact that is not explainable, then one reason may be that it is wrong. And this, of course, is here the case. So I was stupid enough to use my notes, and I made a mistake on my notes. Yeah. So I mean, as a reminder, where we came from. So there was this tau. We were talking about the tau, the mean free time, which is the mean free path divided by the speed at which molecules are moving, which is the speed of sound. And we had then that this tau is proportional to the Newton number times the Mach number. And in this context, I was going to write that tau times the speed of sound square, which we get in the Navier-Stokes equation, is proportional to the Newton number divided by the Mach number, which then we called 1 over the Reynolds number. And this is so because, of course, this is not correct. The speed of sound square is, of course, proportional to 1 over Mach number square. And now, if you put this into here, then it becomes clear that it's the Newton number over Mach number, because otherwise it doesn't end up in the right way. So this was my mistake. Last time, I leave everything on YouTube to prove that I made this mistake, because this is always what people make fun of me. And, when people make fun of me, then at least they talk about me. Okay, so getting to the topic of today, which is over-relaxation. Okay, over-relaxation. And we start with a very important question that you may get along when you tell somebody that you go to a course where they teach Lattice Boltzmann method. Yeah, and if anybody is really into kinetic theory or even in Navier-Stokes, then you would usually get to a question, are you stupid? Yeah, because, the question that we ask is, why is it not insane? Yeah, so I propose that you may be insane to come here. Why is it not insane to solve the Navier-Stokes equation because this is what we actually want to do, the Navier-Stokes equation with a kinetic model. Okay, maybe kinetic models are cool, I don't know, yeah, we just like to do it. The problem with kinetic methods in comparison to continuous methods is that you have this molecular collision and you would have to resolve the molecular collision. Yeah, which you do not need to do if you use a continuous model. So this is our trouble here. Kinetic methods have to resolve the particle collisions. So let's do an order of magnitude, some order of magnitude considerations just to see how stupid we are. Order of magnitude. Okay, what do we have in kinetic theory? We have a pen that is actually writing. We have a mean free path. So I've already said what the mean free path in air is about. You remember? Anybody online? What's the mean free path in air?
It's an average distance.
Yeah.
Okay, now
okay, go for it.
Right. Now, do you want the number?
Yeah, a number in meters.
16 nanometer.
Nanometer, yeah. So I did not understood you very well, but it's nanometers, 16 nanometers roughly. Yeah, depends on the pressure, of course. So then we have the speed of sound. So I guess the speed of sound is about 340 meters per second. Something like that. So then, in order to get, so you could say in order to spatially resolve it, we would have to have this 60, we would have to be much smaller than the 16 nanometers, but we also have to resolve the time. So mean free time you see, this is the PhD students may now associate this with their life. Yeah, the mean free time, the mean time that you have free, your spare time is 1.7 nanoseconds. That's not a very nice life, right? So we would have this is the time that molecules have before they collide again. So this is the time in between the collisions. Yeah. So if this is the time in between collisions, then the time of a collision is of course shorter. The collision time is much shorter than the mean free time. How much is much? I don't know. But see, we are below nanoseconds. And this you have to resolve just because you are so stupid and use a kinetic method. So, is everybody running away now? No, not yet. Okay, say kinetic methods require we have short time steps and very, very short time steps. So now is this true for Lattice Boltzmann? Lattice Boltzmann is always the question, is this actually a kinetic solver? Yeah. Well, so what did we get last time, lecture 4? So this is now a little bit repetition from last time, but it's very important to get this into your mind. So what we derived last time, we had this collision operator, which in that case was a BGK operator, but that's not important. So the collision operator was basically the post-collision case that we always write with this asterisk minus the pre-collision distribution. Yeah, obviously this is the change between before and after is the collision operator. And in the BGK we had here this omega times Fi equilibrium minus F before collision. So this, by the way, this is an explicit algorithm because what we can do is we can take this here, yeah, and then we can directly compute F star, so the after collision. So this is, I say this is algorithmically, it's algorithmically explicit. Meaning we do not need to solve any equations. Yeah, we just put in what we know and we directly get what we are looking for. So, but then we said, as compared to the actual Boltzmann equation, now we have here one F before collision and one F after collision. And the Boltzmann equation, because it's continuous, just have one population, one distribution function F. So is this now the population after collision or the population before collision? Yeah, and it is, as we said, it is neither. We do a change of variables. Again, this is what we had last time already, yeah, so just repetition. So we replace this Fi by Fi half minus Fi star half plus Fi over bar. Yeah, so the Fi over bar, if you rewrite this, the Fi over bar is Fi plus Fi star 1/2. So it's the population in the middle, yeah, between pre and post collision. Now, so if I write my pre-collision thing, my pre-collision population here in this way, what we get is the following. So we can rewrite this operator up here. This is equal now to omega Fi equilibrium. So minus, we are replacing this guy, so we get the overbar version of it. So this is the one that we want to have here because it's the actual distribution. So it is the thing that is in the real BGK equation, yeah, in the real physical BGK equation. And then we have, of course, this Fi minus Fi asterisk 1/2. And you see that this guy here appears here again. So what we are going to do is we put this on the other side because the way it is here, it is not yet explicit. So we want to make it explicit, of course. So we put this on the other side, and we have done this last time, so I write the result, Fi, so we put it back and we get 1 over omega minus 1/2 into Fi equilibrium minus Fi overbar. So now this is now the actual BGK equation with this prefactor being being the actual 1 over tau. Yeah, so then tau becomes 1 over omega minus 1/2. The interesting thing now is that this is implicit for F, okay, I should write it the same way, Fi over bar, yeah, which we defined as, again, this minus this, yeah, so, okay, so this equation here actually is implicit because this Fi over bar contains the F star, which we don't know, yeah, which we want to calculate in this way. But we have not changed what we are actually doing, right? So we still do this up here, yeah? We just rewrite it in the form for the equation that we actually want to solve. Now the interesting thing here is that the equation that we want to solve, we solve this implicitly, but the algorithm, so that the equation that we actually use for solving this implicit thing is an explicit equation. So this here is implicit, and as I said, so we have an explicit algorithm solves an implicit problem. Why is this interesting? If you are familiar with implicit methods, then you know that will always tell you you should use implicit methods because implicit methods have no stability constraints on the time step. I mean, it's a little bit stupid because, yeah, there is no stability constraint, but if you don't resolve your physics, you don't see what's happening, right? So it's not that you can make time steps infinitely large just because you don't have a stability constraint, yeah? So, but the important thing here is that you are not constrained to a time shorter or equal as the collision time. And this makes the big difference. Yeah. So our tau, remember the tau, the mean free time, is now 1 over omega minus 1/2 times the length of a time step. Meaning we can, when we know the physical mean free time, we can, for our implicit method, which I indicate now by writing implicit imp here, yeah, would give us delta t, so we just invert this, tau plus 1/2 delta t. So, and this is like an implicit BGK. So this is what we are using in LBM. I mean, if we use an BGK in LBM, yeah, but we come to this later. So if we didn't had this change of variables and we would solve this directly for the f instead of the f bar, then we would have an explicit scheme, and in this explicit scheme, tau would just be 1 over omega. Yeah, so this, I mean, together with the time step. So omega explicit would be delta t by tau. So this would be an explicit scheme. And there are actually explicit schemes like this to solve the Boltzmann equation. Okay, so now see what happens if delta t would become much larger than tau. Then this omega implicit would go to 2. Yeah, you can easily verify this. Yeah, so tau, yeah, mean free time, very short, then omega goes to 2. In the explicit scheme, obviously, would go to infinity. And this would also mean that you would, in your code, yeah, if you have an explicit BGK solver like this, you also have to multiply, yeah, this difference with a very, very large number. I mean, actually going to infinity, yeah? Multiplications with large numbers are difficult things to do. Let's look at our actual collision operator. That looks like this. We have an Fi after collision is the Fi before collision plus omega Fi equilibrium minus Fi before collision. Say we put omega in the range of 2, then what we are ending up with is that our after collision is 2 times Fi equilibrium minus Fi. And these are numbers of similar size, okay? So even in the limit of infinitely long time steps, you don't get, the numbers always stay in the same range, yeah? So we say they are well conditioned. Even if the time step is much, much larger than tau. So, we call this regime where 2 is larger than omega and which is larger than 1. We call this over-relaxation. Okay, let me try to me see, do we actually have composite? Okay, I'm going to draw, I'm using this stupid tool here to get me in. Can I move this around? Okay, so I've drawn here a circle. I'm going to explain why. So say we are somewhere in in a configuration space, yeah? Say here are different moments. Oops. Why didn't this work? So say here are some, so we are in this configuration space, say we have here some moment 1 and moment 2, yeah? Of our, now we have only 2 moments because the space is very, very large, yeah? So now, I mean, it has many dimensions. Actually, in the proper Boltzmann equations, it would have infinitely many dimensions, but here it has finitely many dimensions. So say in this configuration space, we have somewhere an equilibrium, yeah? So F equilibrium, and we have somewhere the pre-collision state F, yeah? Then what the BGK does is we move from the pre-collision state towards this equilibrium state, yeah? And in an explicit scheme, we would usually end up with the output, say F, so the after collision, somewhere in between the incoming and the outgoing, and the equilibrium. Yeah, so this means we are not colliding everything, yeah, but we are colliding some of them, yeah, to a certain extent. Yeah, so we would go from pre-collision to equilibrium somewhere, and this is called under relaxation. And this is something that we would do if we were to resolve the time scale of a collision. Yeah? So in one collision that we have, we do less, I mean, it means we are doing less than one collision per time step, right? Yeah, so we will end up in between what the incoming population and the equilibrium population. What we can also do is we can go actually up to this point here. Yeah, so this point here would be as much out of equilibrium as the incoming population. So if we end up here, we will have like here would mean that going here would mean that that tau is equal to 0. Yeah, so tau usually is not 0, but it is something in between. So it will not be 0, but it's small, and then we end up in this place here, F, and this is called, there we will be in over relaxation space. So okay, with over relaxation, tau is I mean, if we go further on, if we go to the outside, what is going to be here? When we go to the outside, we imply that tau would be negative, yeah? So because it has its 0 here, it is positive outside here, yeah? So we cannot go outside here, otherwise we would run backward in time, and we know from Boltzmann's, from the ether theorem, that this is difficult to accomplish. It would be very nice if we could do this, but it's difficult to accomplish, because if we could do this, we could look at, you know, a cup of tea at rest and determine when it was. I mean, we turn the time back and it will flow back into the kettle. Yeah, so that's kind of difficult to imagine. Yeah, so. This is the over-relaxation regime, and the good thing with the over-relaxation scheme in the Lattice Boltzmann method is that it is linearly stable. Linearly stable is a bad word because fluid dynamics is not linear, and so it's also not actually stable. Yeah, but it's linearly stable before omega is equal to 0 and excluding actually 2, because then it's only marginally stable. Yeah, there are actually things that are stable. So in fluid dynamics, for example, if you linearize fluid dynamics and you solve just the Stokes equation, which, yeah, okay, Stokes equation is usually a very high viscosity regime, but it's a linearization of the Navier-Stokes equation. So if you have this linear system, yeah, so then it will be stable for omega equal to 2, or just so below 2, yeah. So does this mean that Lattice Boltzmann is always stable? No. I mean, for one reason, it is not linear, and there is, of course, another reason why it's not even stable in the linear case, and this is not unconditionally stable, I would say. So stability bound does not come from collision. There's no stability bound for collision. I mean, other than you cannot use negative relaxation times, mean-free times. Yeah, that obviously doesn't work. But unfortunately, this is not all we have. We also have the streaming, and the streaming has a stability limit. And the stability limit is, of course, the CFL number. CFL condition, let me see. Now, today we have mainly people listening who are, I would say, a little bit more advanced. CFL condition, Courant-Friedrich-Levy condition. Is this familiar? Okay, good, then. So this is a thing that is related to information propagation in an explicit method, and the streaming operation is, of course, an explicit method. Yeah, so information cannot travel faster than a population travels in the streaming step from one lattice node to another lattice node. Yeah, and this basically can be written like this. So we have the velocity on the velocity of the fluid, yeah, plus, so this is not all, plus the speed of sound. These two things together need to be smaller than the lattice velocity, and the lattice velocity is is delta x by delta t. So the important thing to notice here is that propagation of the fluid flow, and the propagation of a sound wave, they are not unrelated to each other, yeah? Because the system is Galilean invariant. This means that if the fluid moves, then the sound wave also moves together with the fluid. So, and this means that on this moving fluid, an added on sound wave cannot propagate with more than one lattice spacing at a time step. And if you try to do it anyway, it will crash your code. And since we are not able to avoid that there are sound waves in the method, yeah, we have to take the limit of the sound waves into consideration. So for the time step, this you can translate this is that the time step must be smaller than the grid spacing divided by the velocity plus the speed of sound. So, for example, I mean, okay, I should say this is a hard limit, yeah? So this is the place where it crashes. You should stay clear for this very substantially if you want to have an accurate result, yeah? So, let's see, what is our hard limit? For, say, we'll simulate delta x is equal to 1 millimeter. And say our velocity should be, okay, say velocity is 0. Then delta t, provided that we use a speed of sound of 340 meters per second, yeah, then we'll end up at roughly 3 by the power of minus 6 seconds. Okay? So if we have a resolution of 1 millimeter, we have a time step of 3 microseconds. Yeah, so which is much better than what we had in nanoseconds and nanometers before. So, but this also implies that we are stringent with the speed of sound, which very often in practice we are not. What we can also do is we can rescaling the Mach number, so using the wrong Mach number, if you will, leads to even larger time steps. So what is often done, if you don't care about acoustics, then you use a high, so you actually use a much higher Mach number than is actually true for your physical problem, yeah, because this usually does not affect that much your performance. Okay, now the answer to the question above, why is it that we are not completely insane to use the Lattice Boltzmann method kinetic solver in a way to solve the Navier-Stokes equation is because it is, no, what I'm writing. So this is still efficient only due to the ability to do over-relaxation. And you will usually see Lattice Boltzmann applied in over-relaxation mode. Everything we do in optimization and so on is always in over-relaxation mode. Actually, if you try it in under-relaxation, it may be very inaccurate. So this is the answer, if you ever asked. Lattice Boltzmann uses over-relaxation. Therefore, our time step is arbitrarily much longer than the collision time, and therefore it is basically compared very, very similar in efficiency to Navier-Stokes solvers. Yeah, so it's the question whether it's more efficient. There's a different question, but from a time step perspective, it is very, very similar to an usual Navier-Stokes solver. So there's a property that some people say I probably myself, I give you a warning because I don't seem to understand this myself very well, but this is my version of it. So there's a kinetic methods tending to the Navier-Stokes equation for the case that we have been looking at. So delta T is much larger than tau. They are called asymptotic preserving. So asymptotic preservation, is the following concept. Asymptotic So there's also other things that are asymptotically preserving. There's not necessarily something that only applies to the Lattice Boltzmann method and other kinetic methods. The idea is the following: we have the possibility to first discretize something and, okay, let me draw the picture, maybe it's better. So let's say we have Lattice Boltzmann, we have a discrete Boltzmann equation, yeah, with discrete speeds on one hand side. And we have the actual Boltzmann equation on the other side. So then in order for the discrete Boltzmann equation to be correct, we would have to say that if we make the time step going to 0 and the grid spacing going to 0, yeah, so we want to see convergence, yeah, smallness parameter small, we go from the discrete version to the continuum version. Otherwise, we do something wrong. So this is now one path, and this discrete Boltzmann equation, let's say the picture is going on, we can also use here these physical parameters where we said the Knudsen number is going to 0. Yeah, so it's the same thing here. Maybe I start here. The Knudsen number square, yeah, as we said in lecture 2 or so, yeah, if Knudsen number square is going to 0, while the Knudsen number is larger than 0, we end up with the Navier-Stokes equation. Yeah, coming from the Boltzmann equation with this physical under these physical conditions, yeah, so this is now still the compressible Navier-Stokes equation. We can also make the Mach number going to 0, then we end up at the incompressible Navier-Stokes equation, yeah? So, and on the other side, we can take a discrete Boltzmann equation, discretized for the Knudsen number square equal to 0, and the Knudsen number still larger than 0. So the same thing. So this is a simplification of the discrete Boltzmann equation. Yeah? So the discrete Boltzmann equation saying that we have infinitely many discrete speeds. Yeah? And now we simplify this to only a few number of speeds. So from the discrete Boltzmann equation, we come with this simplification to the Lattice Boltzmann equation, and from the Boltzmann equation we come to the Navier-Stokes equation. And now the idea is that if now we do the same thing here, we do the time step getting smaller and the grid spacing getting smaller, we end up at the Navier-Stokes equation. And the concept of asymptotic preservation is that we can go, so to speak, in the different ways, yeah, from the discrete Boltzmann equation to the Boltzmann equation to the Navier-Stokes equation, or from a discrete Boltzmann equation with the small Knudsen number to the LBM, and so to the Navier-Stokes equation, yeah, so that we come from two different parts to the same Navier-Stokes equation. This is what we call asymptotic preservation. Okay. This is a little bit of theory. It doesn't have that many. Okay, I should not say it does not have practical implications. I mean, it has the practical implication that we can use a discretization of the Boltzmann equation, the Lattice Boltzmann equation, to actually solve the Navier-Stokes equation. Yeah, this form of the discretization of the Boltzmann equation cannot be used to solve the Boltzmann equation, because you see, it has already the simplification of the Knudsen number square being 0 built in. Yeah, so you cannot use the Lattice Boltzmann equation to solve the Boltzmann equation. Yeah, so this is the maybe. Okay, let's write down some notes. So LBM has the same time step constraints as an explicit Navier-Stokes equation solver. And as I just tried to say, there is no kinetic physics, if you will, if delta t is much larger than tau, which basically is also related to Knudsen numbers square being to 0. Yeah. So with this assumption, with doing over relaxation, and with this Knudsen number square being going to 0, you've eliminated the kinetic part of the Boltzmann equation from it. Yeah. There's no way you can use this for solving the actual Boltzmann equation anymore. So, I mean, whenever you come across, like Sarosuchi probably is saying, we have better physics with doing Lattice Boltzmann. This is extremely questionable what you mean by better physics. Yeah, of course, the Boltzmann equation, it has better physics than the Navier-Stokes equation. There is no question about this. But this part of the better physics, when you go to the Lattice Boltzmann equation, you have eliminated it. Yeah. So don't make any statements of superiority based on kinetic physics. There is one thing that is actually lived, which we sometimes call kinetic legacy. And this is more like a practical thing. We have we still have a linear advection operator. The linear advection operator means we can still use simple streaming, a simple streaming operator. So the linear advection operator, this leads sometimes to the statement that you will probably hear somewhere, is that all nonlinearity So the nonlinearity in the lattice Boltzmann equation is in calculating the equilibrium function. Yeah, so it's in the collision operator. Yeah, so all nonlinearity is local because the collision operator is local. All non-locality is linear. So in the Navier-Stokes equation, the nonlinearity is in the advection operator. The advection operator and the collision operator, as we saw, the collision operator is actually the diffusion operator. And this is something that I find very, very funny and kind of interesting, because the diffusion in the Navier-Stokes equation is the thing that is linear, obviously, yeah? And the advection is the thing that is nonlinear. In the lattice Boltzmann equation, as in the Boltzmann equation, this is why it's the kinetic legacy. In the Boltzmann equation and in the lattice Boltzmann equation, the collision, which corresponds to the diffusion, is non-linear, whereas the advection is linear. Yeah. So, and in the Navier-Stokes equation, the non-local part, the advection part, is the thing that is not linear. So we have the advantage, non-linearity local, non-locality linear. Okay, so this is an actually advantage. Good. Did I convince you?
Yes. Just a question. So
Yeah.
what you just said is that it's the opposite in Navier-Stokes and between Lattice Boltzmann.
Yes.
And here, for example, non-linearity local, it's because of the collisions.
Yeah, the non-linearity is in the collision. It's only when you compute the equilibrium.
And what about non-locality?
The non-locality is the streaming.
Okay.
Yeah.
Okay.
And this is very simple.
So that is for the Boltzmann equation.
This is for the Boltzmann, and this is what we get from starting with the Boltzmann equation. Yeah. Now, because I spent now half an hour telling you that basically it is lattice Boltzmann in principle is as good as using finite differences. Yeah, and maybe it is. Yeah, but there's one thing that we get out of the kinetic theory, and this is this sentence here. Yeah, all nonlinearity is local, and all non-locality is linear, which of course is not a sentence. Okay. Going practical. The thing that is non-linear is the collision operator, and in this in particular, the equilibrium function. And let's say equilibrium functions, because you have different options. Even for BGK, you have different options. And by the way, you have other options than BGK. So the options that we are talking about today is moment matching, Taylor expansion, and I have to put this into quotes, entropic. Okay, these are the ones we're going to talk about. Let's start with moment matching. Okay, usually say there's a didactical concept to go from the stupidest one to the best one. That's not what I'm going to do here. So they are kind of in random order. Yeah. Actually, moment matching. You should listen to moment matching because this is the best one. This is the one that you should use. Okay. So let's say we go to 2 dimensions, and in these 2 dimensions, we use our lately introduced Miller indices, yeah, where we write the populations like this. So, sorry, now I get F1, 0, F minus 1, 0, F1, 1, and F minus 1, minus 1. Did we get all of them? Say 1, minus 1, F minus 1, 1, right? So if we want to compute moments here, we will have 2 indices, MB, and we take the sum over I and J, Fij, yeah? So here we use always, okay, most of the time we use 2 indices, yeah? This makes life much, much easier than to use 1 indice, even though you may write, how are they doing this in the book? With 2 indices, yeah. So they're a little bit more modern, yeah. But the book is from 2015, yeah. This is now getting 10 years old, yeah. So, right. So for the, we are looking for the equilibria. If we have a conserved moment, let's say this is a conserved moment, then we know that the moment is equal to its equilibrium, right? They're conserved moments. So what conserved moments do we have? We have M00, which we call the density rho. We have M10, which is this rho times ux. And we have M01, which is rho times uy. So I hope you are already familiar now with these things. So these are the conserved ones. So 3 conserved ones. Energy is not conserved according to the Navier-Stokes equation. Yeah, Knudsen number square going to 0. So we do not conserve energy here. Still, we have the second order moments, M eq equilibrium. So moment matching means we are matching these things to the Maxwell equilibrium, and we've already computed this several times. We have rho, density, c s square, speed of sound, plus ux square. M02 equilibrium is rho cs square, speed of sound, plus uy square. So this comes out of the Maxwell distribution. Then we have the moment MEQ equal to rho ux uy. Been talking too much stupid things. Let's see, I'm going to take over time. But actually, I have to remind you, actually, this is a 3-hour, so I'm always allowed to take over time here. So, okay, we have M11 equilibrium, and the way we actually get this, now a little bit without much explanation, the way the Maxwell equilibrium is actually constructed. It is a Gaussian distribution, right? And the thing with the Gaussian distribution is it is the state in which everything is kind of independent of each other. Yeah, so if everything is random, then everything is independent of each other. So the coordinate, the x coordinate is independent of the y coordinate, right? So, and because these are probability functions, it means that the probability of picking a particle, measuring its x velocity is independent of measuring its y velocity. Yeah, this is what the equilibrium actually states. And if these things in the different directions are independent of each other, that means that their probability to finding it in this state in x and in y is just the product of finding it in x and in y. And this obviously also applies to the moments then, right? And this means that the moment, the equilibrium of M11 equilibrium must be the product of these two individuals, M01 times M10. However, with one caveat, namely that these moments are not normalized. Usually, a probability distribution is normalized to 1, which we have not done here. So we have to divide this again by rho, okay? So this can actually be applied to all the other moments too, namely, the moment M12 equilibrium must be M01 times M02, but M02 is not necessarily in equilibrium, therefore we write here equilibrium. Yeah? We'll later see that whether equilibrium or not equilibrium, this is actually an interesting question, but if we suppose everything in equilibrium is in equilibrium, then obviously this would also be equilibrium. Yeah? So, and this can be written as rho ux cs square plus uy square. Yeah, and by the way, if you take the third order moment from the Maxwell-Boltzmann distribution, exactly this comes out, of course, because this is how the Maxwell-Boltzmann distribution is constructed. Yeah, finding the x component independent of the y component. Yeah, so then this is obvious result of this. Okay, so then obviously this here looks like this, divided by rho. So rho, I mean, the advantage of this is that just by knowing that, you can immediately write these things down, right? Without doing these lengthy calculations. Uy cs square plus ux, right? So, and therefore I can now give you the challenge. What is M22 equilibrium?
Is M2 equilibrium times M20 equilibrium times M02 equilibrium. And that's going to be.
So divided by rho is very important.
And that's going to be rho squared, right? Wouldn't it be? Oh well, rho squared.
Rho square.
Yes, because we are. No, so it's.
No, you can.
CS.
So never rho square. So usually, you see, all these probability things are only applied for normalized distribution functions. Yeah. So because we have not normalized it, we have always to, when we have a product of two moments, we have to divide once. So if we had a product of three moments, we would have divided by twice of this. Yes. So in the end, all of them have rho in front.
Okay.
Yeah. So rho times
CS squared plus ux squared times CS squared plus uy squared.
You see, it would take you a lot of time to solve this integral, right?
Yes.
And you can simply write it down by just knowing where stuff is coming from.
I think there's just a mistake.
Okay, yeah.
In the second line, it's like M10 and not M01 in the second equation.
The second, wait, here's,
Yeah.
here,
Yeah, it's like M01, no? Or am I wrong?
yes, thank you very much, yeah. 01, yeah, of course. Right, so these are the nine moments. So we have 9, okay, this is D2, Q9. We have 9 distributions. Now we have set 9 moments, yeah? Let's see, what is the time? So in this, yeah, so because this is the simplified thing, we have some third order, okay, some third order in velocity. So the order is in velocity. Terms are missing. So we find that nowhere we have ux cube. Yeah, that just doesn't appear here. Yeah, but we have some terms that are of higher order. For example, this fourth order term. This actually, no present. All of this actually leads to an anisotropic equilibrium. Okay, I'm saying this because I had lots of discussion with Pierre Lallemand. Pierre Lallemand is one of the guys who invented the Lattice Boltzmann method, more or less. And I was asking why he's using only terms to second order, and yeah, he agreed that this here is the more stable thing, but this leads to an anisotropic equilibrium because we have these missing parts, and he prefers to have an isotropic equilibrium. So whether this makes sense to prefer it, I don't know, but this is, I just wanted to tell you that this is the reason why there are people not using this, okay? And these people are actually the inventors of everything, and so they wrote everything down. So if you look in the book, you will not see this equilibrium, usually. Or somebody tells you, oh, this is my clever invention, but I mean, it was always been around. So, okay, what I'm not going to do, if you really like it, you can use your computer algebra skills or your hand algebra skills to just solve this for the distribution function, so you get lengthy equations, yeah, that include terms up to fourth order here, yeah. The thing that you will find in the book is the Taylor expansion. I mean, not only in the one book, but in the books. So the Taylor expansion equilibrium of the Maxwell-Boltzmann distribution. So okay, if you do a Taylor expansion, you should actually get, mathematics should be consistent, yeah? So you should get the same thing as here. So the reason why you don't get the same thing as here, because the Taylor expansion does not care about what moments you are looking at, right? So you would have to you would have to consider in your Taylor expansion to what moment you are going. If you just do a Taylor expansion, it will give you, an arbitrary equilibrium. So anyway, you have to cut it off, and you have to cut it off before you run out of moments. Yeah? Otherwise, you are crashing your system. So then the place where they cut off is at second order. which is before. Yeah, this is before you run out of moments. So they will only contain terms up to order 2. So if you look back into our moment matching thing, yeah, so there are these terms to second order, they will all appear, but all these things to third order, they will just be cut out. Yeah, and actually we get the same equilibrium just by, when we use moment matching, just by cutting out everything that is above second order. Yeah, so this will give you the same result. And the result that we get is, if I've written it down correctly, but don't nail me down on this, you can look in the book. By the way, one thing that annoys me with many of these papers, in particular when they come out of China, I think they don't properly learn European letters. They often put an omega as the weight here. Yeah, this should be a W, not an omega. Yeah, don't do this in my homework, okay? Yeah. So W, because it's a weight. Yeah. An omega is an O, not an W. Yeah, it's not a proper way to write a weight. Wi rho 1 plus. Okay. By the way, I used the version as originally written down with one index. Yeah, where we have an E directional vector times the velocity vector, and this divided by c square. The annoying thing here again is that this does not look like dimensionally consistent. Cs by the power of 4 minus u square. So u square, okay, let's write u times u, right? Divided by 2 times cs square. So this doesn't actually look like dimensionally consistent, but there must be here somehow a c square in front, which apparently has disappeared out of literature. Wi are the weights obtained at velocity 0 and rho equals to 1. So I will not give them here. Maybe I should, in order to give a complete course on Lattice Boltzmann, I should do this. My observation is that in the homework, so far all students used this thing here, even though I always tell them this is the worst solution then you can use, and even though I don't give the exact numbers, you'll find them somewhere. Look at Wikipedia, for example. Yeah, this is easy to find. So I don't want to encourage you to use this. It's just the usual nonsense around. So the reason why Pierre Lallemand told me to use this is an isotropic equilibrium for whatever it's good. Isotropic. It's isotropic, but then it is missing higher order terms in velocity, and when we'll ever have a Lattice Boltzmann course second semester, I will tell you in detail what this missing higher order terms actually does. Yeah, but here we'll just leave it at that. You will find this thing in the textbook. It's the classical textbook version, even 20 years ago, when the only two textbooks were the one by Saurosuchi and what was the other one? Wolf Klatrow, yeah. 25 years ago. Wolf Klatrow, 25 years ago, yeah. So, there you can read these things. What? No, textbooks. I missed my line. Sorry. This is, you should never write from notes. Classical textbook equilibrium. Oh my God. So, okay, my warning that I gave you, yeah, it's of course the simplest thing to just pull something from the book, implement it, and it's also the shortest, of course. You can hardly simplify on this anymore, but this is becoming increasingly unpopular. I mean, depends on what you are doing. If you're only doing very low Reynolds number flow, yeah. So I've seen the guys doing blood flow. Sometimes they still love this. But I mean, one thing is it is less accurate, and then moment matching, and the moment matching in particular has much better stability. And with much better, I mean really much, much, much better. Actually pretty stupid to use this version. Oh my God. Okay, we'll have a 3-hour lecture. Entropy.
I have a question.
Yes.
So the Taylor expanded is less popular because it is...
No, it's becoming, in literature, it's becoming less popular. It's actually still relatively popular. Yeah?
But it's less popular due to...
No, it's becoming less. Okay, so if you... I mean, it is known for ages, yeah, but using the higher order equilibrium gives you a more stable method. But it's not known to everybody.
Okay.
Yeah? So this is why I'm here, I'm telling you, but you see, we have how many? We have 4 people attending the lecture. Maybe 10 later will watch the video. Yeah? So they all need to be told this is not very stable. Depends on what you want to do. Maybe you are lazy and you don't care about that, you know, in your problem it's stable enough. Okay, fair enough. Yeah?
Okay, now yes, okay. So sorry, what I didn't understand was that it's the much better stability of the moment match method.
Yes.
Okay, yes, now.
So you should use moment matching. I mean, you should not use BGK at all, by the way, but we'll come to this later. But if you use BGK, then at least use moment matching. So, entropic equilibrium, and this comes out of Zurich, Ilya Kalin and Antosh Anzumali, I believe, yes. Actually, it's Antosh Anzumali and Ilya Kalin was only the advisor. So I'm certainly messing this up. I'm just writing it from my notes. So we have plus CS. Okay, I'm trying to use their notation. C minus U alpha by the power of C alpha divided by C, where alpha is either x velocity or y. velocity. So, and c is of course delta x by delta t. And this s alpha is equal to the square root 1 plus u by cs, where cs is the usual speed of sound square. Okay, I do not pretend that I understand this thing, but I recently attended a talk by Ilya Kalin, who was giving, after 18 years in existence, he gave an explanation what it actually does. So for the previous 18 years, it was a little bit obscure what this is supposed to do. Now I learned that the idea behind this is that with this we can kind of stretch in the CFL condition. And the way this is done is by lowering the speed of sound. So usually we said that the speed of sound needs to have a specific value in the Lattice Boltzmann method to get the third order moments correct, yeah, and to get isotropic viscosity by this. And this method here starts with the correct speed of sound, but if the velocity is getting higher, it lowers the speed of sound, and it actually lowers the speed of sound until it becomes 0 for very high velocities, apparently, yeah? So you remember we have u plus cs must be smaller than c. So if you make cs getting smaller with increasing u, you can stretch the CFL condition and you stay more stable, yeah? So, because here, okay, so I should say probably, okay, maybe this is kind of annoying, because this here is a constant, this here now is not, yeah? Maybe I write, I put something on it in order to imply this. So cs is, which is the actual speed of sound, is not constant, but it is a decreasing function of the magnitude of u. So the idea is to make the idea behind this entropic thing is to make your simulation more stable. I mean, if you stretch the CFL condition, you make the speed of sound lower, yeah, then you can get the velocity higher before you crash the CFL condition. In my opinion, I'm sorry, this is bullshit, because I mean, still you're limited by the CFL condition, and CS usually is 1 over square root 3. So basically, what you can, so which is roughly a half, right? So basically, what you can do, you can scratch the CFL condition to twice as much by completely killing physics. Yeah, I mean, you are changing the speed of sound. You are killing physics. You make your viscosity anisotropic in the process. So, and all you reach is you increase the CFL condition by twice, which is the same as if you take half the time step. So, okay, which you could say now you can simulate twice as fast with not keeping physics but keeping stability. But then doing your computation only twice as fast is not really a fundamental improvement in speed. Yeah, therefore I don't get it. But this is kind of.
I have a question.
I don't know. Okay, does YouTube kill the video because I said this B word? Maybe.
But then that means that the CFL condition is increased.
Yeah. So you get this guy here smaller. Yeah. So then, yeah.
That doesn't mean that the velocity can get higher than 1.1.
This. No. The velocity must be smaller than 1.
Okay.
Yeah, of course it has to be smaller than 1. So in the normal case it would be smaller than 1 minus 1 over square root 3, which is roughly 0.4 something.
Okay.
Yeah, and here it can go to 0.9 perhaps.
Okay.
Yeah, this is what you get. You can double it. Yeah. In theory. So the thing is, they call this entropic in order to imply that this has anything to do with physics, which it has not. I mean, in physics, you don't change the speed of sound. So entropic. This is not a physically accurate. By the way, everything is fine with this method. I mean, when I say it's not an accurate approach, I mean I'm potentially too stringent here. As long as the velocity is small for this model, where the other one would also be stable, this is completely fine. Yeah, because then the speed of sound is roughly constant, and it behaves the same way as the moment matching would also behave. Yeah, so it's not that this model is completely is giving wrong results. It's just the point that it is better than something else is kind of questionable. So it's changing the speed of sound can only double the stability range. So it basically, you would give the same thing when you take half the time step. Sorry. So it's a matter of taste whether you think this is a meaningful improvement or not. In my opinion, it's not a meaningful improvement. Okay, so you guys, do you have time and interest in? Okay, then we go to lattice. So finally, I do my 3 hours that I'm getting paid for. Lattice in 3D. Okay, we always start from a one-dimensional lattice, yeah, so where we have this f0, f1, and f minus 1. So this is our 1D example. And we call this D1Q3 lattice, yeah, so this is what we had last week. And one thing to get to higher lattices is going higher dimensions is to use a tensor product lattice. Tensor product lattice, where we have D3, for example, Q3 by the power of 3. which then we call D3Q27. So, and now let us look at the countable moments here for this lattice. Countable moments in 3D. So let's say we have one zero moment, one zero order moment. Yeah. So this is M000. Yeah. This, of course, we have only once, one permutation of these. Yeah. So then first order. I'm not going to write moments here again and again. Is we have 1, 0, 0, and here we have, of course, this 3 times, 3 permutations of this. You know what I mean, right? So then second moments, what do we have in second moments? We have 2, 0, 0. Out of these, we have obviously 3 permutations. And then we have M1, 1, 0. How many permutations of this? Okay, I've already written it. Yeah, 3 permutations, 2. So we have six second order moments. So what first order moments do we have on this lattice? We have, why do I, countable, sorry, shouldn't we go on with third order moments in between? Makes sense, right? So what third order moments do we have? We have, okay, give me an example.
Third order?
Yeah.
3, 0, 0.
Okay, do we have this?
Do we have this?
I mean, did we have this in 1D? Because we have talked about a lot about the...
No, because it was related with the... Was it related with the energy? No, because it was not independent, right?
It was not independent, yeah? So now we don't have this. So what instead do we have?
1,
1,
1, 1.
1, 1. How many permutations of 1, 1, 1?
1.
You notice this sentence. 1, 1, 1, 1, 1. 1, 1, 1, 1, 1.
Yes.
Now, what do you know what this means?
No.
Do you know what it means? 1 Smith, $1, $2. 1 Smith, a guy called Smith. $1, $2. So now, you know, there is a Korean guy who is called Won, and the Korean currency is won, and he won only one. So 1, 1, 1, 1, 1. Yeah? Okay, so 1. So, we're running out of time and I'm talking stupid. What else?
2, 1, 0.
2, 1, 0. How many permutations?
3? No. 2, 1, 0, 2, 0, 1. 2. Right?
2 permutations.
Yes. 2, no, because there's also, I need to count that. 0, 1, 2. It would be N.
Okay, now if you start counting them,
Yes.
so I mean, so we can place the 0 somewhere else, and we have to exchange the 2 and the 1. Yeah. So it will be 6 of them.
3 times 2.
Yeah.
Okay.
So 6 is 6 out of them.
But it's factorial, right? So we can get them, or the permutation can be, so in this case we have 3 indexes because they are all independent, so it can be 3 factorial.
Okay, I've not looked at it this way, but yeah, it is 3 factorial is 6.
Okay.
Would be consistent.
Okay.
Yeah. So okay, but good point. I have not. So does this work for the fourth level? So here we have 2. So we have 2 independent ones. So it's 2 so if it's 2 factorial. Wait, no, what are you saying now? Okay, I don't know your method, but out of these we can put the 3 in the 0 in 3 different places. So we'll have 3 permutations, right? Yeah, and then we also have M211, out of which we also have 3 permutations. Because we can put the 2 somewhere else.
Yes.
So, fifth. So we have 2, 2, 1. So obviously we can put the 1 in 3 different places, which gives us 3. And then we have 1 left, which is 1 permutation. And if you add them up, you get 27. So these are the independent moments that we have here. So then we know from the Navier-Stokes equation, so we need the full moments. Full moments, I mean non-equilibrium plus equilibrium up to second moments, right? So you remember lecture 3, where we had this. So, and there also in lecture 3, we saw that we need the equilibrium of the third order moments. Do you remember that?
Full moments on equilibrium plus up to second moments require equation. Yes.
Okay. So, which means, so these are the things that we absolutely need. Here we need equilibria, and then there are things left which are apparently non-essential. And these non-essential moments they are given a name, they are called ghost moments. Or I will just call them ghosts. Okay, ghost, I think probably in literature they most often say ghost moments, yeah? Let's just say I'm calling them ghosts. So, they are non-essential. This is, and if we call something ghost, it's something probably we don't like them. Ghosts are often considered a waste of memory. I mean, we have to store them. And the other thing is we also have to relax them. Yeah, we have to do something with them. And so there are things that are not supposed to be there, so they may be potentially a risk for our stability. Most people don't like ghosts in their house, right? So then this leads to attempts to get rid of them.
Maybe by writing them in terms of the ones of whether they have, because they are.
No. I mean, this is not getting rid of them. Yeah, of course you want to write it down. You know, why do we have ghosts?
Because it's up to the third.
No, why don't we choose a lattice that just has moments up to third order? I mean, why do we choose a velocity set that has more moments than we need?
Why do we choose?
Yeah, so why did we choose this? I mean, we can use another one, and this is what we are usually doing. What has been done, say, okay, we are not usually doing this, but we're using pruning. You see. So, pruning. I don't know whether you want to draw this picture now, but I give it, I didn't want to, I mean, you can download the slides later, yeah? So, we usually start, so the tensor product is on the left, yeah? D3Q27. Now what you can do, pruning, is meaning you're cutting off branches, yeah? So you can cut out the ones that go in the diagonal, and you still have enough moments left in order to solve the Navier-Stokes equation. This is then called the D3Q19 lattice. Or you can cut off what is here the red one, that are the ones that are ending on the edges, and keep the one that going to the corners. This is the D3Q15 lattice. Or you can only keep the ones that end up on the edges and together with the zero velocity, yeah, and this is then called the D3Q13. Yeah, all of these are possible ways to solve the Navier-Stokes equation. All of them are worse than the D3Q27, by the way. So, and by the way, all of them still have ghost moments. You cannot completely eliminate the ghost moments. Yeah, because you get the ghost moments, so you cannot, I mean, there are 10 hydrodynamic, okay, we can go back anyway, we are taking so much over time, so don't bother. So we have in here, let me see, we'll have, do we need them? Yes, we need them. So these are 6, 9, 10. Yeah? So these are the ones that are really necessary. Yeah? And the other ones can be expressed, the third order ones can be expressed in terms of these. So then what you would like to have is a lattice with 10 speeds. Yeah? But it's difficult to find a symmetric set of velocities on a lattice that is equal to 10. So the smallest that has been found was 13, which means that this thing here has 3 ghost moments. Yeah? Okay, so we always have some kinds of ghosts. Okay, let me write this down. Number of moments, the number of moments is always infinite, right? The number of independent moments is immer, is always linked to the number of velocities that we have. Equal to the number of lattice speeds. So the dependent moments, obviously, they can be just calculated from the independent moments. So of lower order. So this means they basically, the higher order moments have another name. So basically there is an alias. And because we call the useless moments, we call them ghosts, we call the ones that are repeating, we call them aliens. Because they cause aliasing. I think this is not in the book. The ghosts are in the book, the aliens are not in the book. But anyway, we use them here. So let's talk about aliens. So in D3Q27, we have MABC equal to the sum over I, J, K, Fi, I, J, K, I by the power of A, J by the power of B, K by the power of C. So in this, we have the moments M220. This one, this is a ghost, yeah, because it is higher than third order. M33, so this here, because we have speeds only -1, 0, +1, this is equal to this one, and this is therefore an alien. The moment 3, 2, 1 is 3, 2, 0 is equal to M, not M120. This is an alien and a ghost. Okay, just for the nomenclature. Independent moments on another lattice I'm sometimes asked how this is actually done. My answer would be look at it and you know, but this is not a satisfactory answer. So for D3Q19 lattice, what independent moments do we have? There's an M00. Obviously, we have the ones that we need. Otherwise, it would not be possible to solve the Navier-Stokes equation with this guy. So we'll end up with these 10 here, plus then we have some third order moments, 6 of them, and three fourth order moments. Okay. A little bit the problem here is that there is no simple method to determine independent moments. I mean, no very simple methods, say. It's not terribly difficult either, yeah? So, I mean, the way how has it been done? I mean, it's not simple. The thing is, because they usually use Taylor expanded equilibrium and strange ways of finding moments. I think it took amazingly long to determine what moments fit to the D3Q19 lattice, even after it has long been there. Yeah. So one way of finding them is using some vector operations, and these vector operations are usually done, are classically done with the one index methods that you will find in many works. Yeah. So actually, most classical works that describe things use an arbitrary enumeration of the directions. Yeah. So classically, we didn't use the 3-index notation. The community didn't use 3-index notation, but they use an arbitrary enumeration, and the older guys are still using this sort of thing. So of the populations, of course. And this basically comes from everybody who likes to work with matrices, yeah, and vectors. So if you want to have a vector, what you do is you say you have a vector f with index alpha, where alpha is an element of 1 to q, where q would in this case be 19 for a 19 velocity lattice, right? And then you say that each of these has the velocity cx alpha, cy alpha, and cz alpha. Yeah, so you specify this vector in your arbitrary enumeration, and then you can actually get back to your to your speeds. And actually, if you implement the Lattice Boltzmann code, you would usually do this. Yeah, find an arbitrary enumeration of your, I mean, either you give them explicit names or you'll put them in a vector, and then you'll have an arbitrary enumeration. So if you have these, so how do you actually compute raw countable moments? So MABC then becomes the sum over alpha F alpha, and this is multiplied by E x alpha by the power of A, E y alpha by the power of B, and E z alpha by the power of Z. Yeah, so this is doing the same thing that we had before. So, and now if we have it like this, we can write these things here, and the speed, the f's and the speeds, or this, was it not the speeds, this would be y. So this here and this here, we can write this as vectors. And when we write them as vectors, we can do linear algebra with them, which some people like to do. So, and then, so there have been physicists coming around, so we want to put them into vectors and use the Dirac notation from quantum mechanics, right? So they use pra-ket notation, so they have a pra where we put in here P, A, B, C as a pra, which is a row vector. No, a lying, what is it? The lying and the standing vector. This is a row vector, right? It's a row vector with the component EX1 alpha by the power of A, EY 1 by the power of B, EZ 1 by the power of C. So here the parameters A, B, C, right? And this goes on until E x q by the power of A, E y, so there's a comma here, yeah, y q by the power of B, E z q by the power of C. So this is in this pra, and then we put the populations in a ket vector, and a ket is a column. This is from F1 to FQ. It's like this, and then you can compute the moments M, A, B, C simply by writing P, A, B, C. So the pra times the ket, which is this scalar product that you use. Yeah, so you're smiling, yeah, because this is what you will what of course you will find in literature. I don't know, did they put this into the book? I guess not.
That's what I'm trying to.
That's what you're trying to put on the, yeah. So this here is basically our moment generating vector. Okay. I'm not very fond of this notation, so you see it's not in my lecture usually, but you'll certainly find this if you go into literature. So, and this is the framework in which they determine which moments can be sorted out as independent. I mean, the point, of course, is this is not unique what moments you count as independent, but you want to determine the independent moments as low as possible, yeah, because they repeat, yeah. So you could also use a higher one, but this doesn't make sense. You want to have the low ones. So what they do with linear algebra then is to check if the moment vector that is in here P, B, C, so this pra is linearly independent of all, so the combination of all moments vectors of lower order, and by order we mean the sum of A, B, C. This is the order. So if they are linearly independent, we get an independent moment. And not independent, that also the moment is not independent. It's not independent, and it means we have an alien moment. So, and with this I have taken half an hour overtime. People are still around. I'm really amazed, but I will now stop the recording.